How's it going, everybody? And welcome back to our Cisco Enterprise series. In this video, we are going to be taking a look at EIGRP. So let me go ahead and clear this off real quick. So I'm using the blueprint here as a guide to what we're going to be covering, just at least you guys know how this is actually going to work. So the flow that we're going to go through is it's semi-important to understand it. Let me go ahead and zoom in here a little bit on it just so that it's easier for you guys to see. So conceptually speaking, in this video we're going to focus on EIGRP at a high level. And I'm going to be putting in the description a link to a Google Drive that's going to have all of the notes that I have. I'm going to put them in the Google Drive. You'll be able to download the notes. So if you're interested in the notes that I've taken, they will be available to you to download and use for your reference. So this is going to be the blueprint flow. The beginning portion of this, so 1.3a, b, c, and d, we will be covering in this section of videos. It probably shouldn't be too many. I'm guessing probably 6 or so to cover all the different topics that I want to go through. So maybe 7. I won't put an actual number on the amount of videos. But the key thing is we'll be focusing on main EIGRP operations. So we'll be getting it stood up and all that good stuff that goes along with it. We'll do a Wireshark breakdown. We'll do a debug so you guys can see the behind the scenes type of stuff, that all the good stuff that goes along with that. Once we get, and I'll go ahead and minimize this, and I will scoot out here a little bit in our topology. My goal with all of the IGP stuff is to go through and use this little topology here for EIGRP, this one to do basic OSPF. So basically start you off at the CCNA level and build you up a little bit so you would understand how to get EIGRP working, how to verify it, that type of stuff. Understand what it looks like from a Wireshark perspective, understand how to debug it, some basic stuff, right? So again, CCNA level introduction. So it's probably going to be a little bit more than CCNA because I'm a big believer in doing debugs whenever I'm when I'm explaining how something works. I'm not a fan of to me, just doing like a network statement and then doing a couple of basic EIGRP show commands isn't good enough. Especially if you're looking to pass an exam, you really need to know how the protocol works. So I'm going to do my best to try to take my knowledge of the protocols and convey that to you guys. And, I've had to go through and debug a lot to try to figure out what's going on. So I'll be doing the same thing. So if I feel like you need a debug, it might be a little bit more than what you're used to, but the way that I was brought up in the industry, my instructors were big on debugs. So I was shown how to do it. That helped me understand it. Hopefully that'll help you understand it as well. So that is going to be the game plan for this. So we're going to go through all of this stuff. So everything here is what we're going to be covering in this section. So what that means is any of the more advanced topics will be handled at a later point in time. So my goal is to get, basic EIGRP, basic OSPF, get them all working. Then we're going to dive into BGP after that. The intention is to get all of the ISP stuff operational so that we, being internet connectivity, we'll go through and then we'll start taking a look at like overlay technologies. How do you use DMVPN? How do you use IPsec VPN? Then there will be get MPLS VPN working, stuff like that. So it'll be a deep dive. We're going to be taking a lot of time into BGP because of the complexities of the protocol. We're going to be doing I'm not trying to make this like an overview of what we're going to be diving into, but that's my intention, is to use EIGRP, OSPF, and get those working. And then when we get into more larger designs where we're looking at things like DMVPN, FlexVPN, things like that, where we're doing overlays with tunnels and GRE and all that stuff, where the stretch of the implementation is bigger, then we'll dive into rounding out the section with like query propagation boundaries and stuff like that. So we'll take a look at how that'll come into play, and leak mapping and summary routes and EIGRP stubs and leak maps and that type of stuff. That's what we'll be taking a look at. So just so you have an idea of what how the flow is going to be. So I am not a big fan of let's put out 10 routers on a topology and then work our way through all the different bells and whistles. Because to me, if you're going to do that, there's technically nothing wrong with it. That's how I learned how it worked. But as time progressed, not everything is going to be a 10 router deployment. So I prefer to show you guys the basics in a much smaller topology. And then as the topology gets more complex, then show you where certain capabilities make more sense. Not to say that they couldn't be done in a 10 router topology, just I choose to do things a little bit differently than that. With that being said, I'm going to bring over my notes for all the different routing protocols, starting with eGRIP. Yes, EIGRP is our fun way of playing around with it. So I'm going to walk you through a high-level overview of how EIGRP works and all that good stuff that goes along with it, and we're going to go from there. So without any further ado, let's go ahead and dive into this. So let me zoom in just a little bit so you guys don't have to sit there and squint. So EIGRP is Cisco proprietary, for the most part. I really should update this and say, sort of. There are some open standards variations out there. Some other vendors have taken EIGRP as well, but for the most part, not so much. EIGRP is still mainly a Cisco protocol. It does both distance vector and link state, which makes it an advanced distance vector protocol. It's not only distance vector, it's advanced distance vector because it supports classless networking, which means, unlike RIP, which will, if you have auto summarization turned on, like if you run RIP version 1, you're going to get just the classful range. You're going to get the 10net, the 172.16, and then the 192.168, and you'll have to understand how RFC19 addressing works for IPv4 unicast in order for that type of stuff to work. Where in RIP version 2, it's classless, which means you can turn off auto summarization, and then you'll get the variable link subnet mask or the VLSMs and summarization. So it supports both manual and automatic summarization. So if you want to auto summarize, be my guest. However, the cool thing about EIGRP is there's no defined hierarchy like there is in OSPF, where OSPF has area 0 and then you have non-backbone areas that connect to area 0. And then with IS to IS, you have your level 2 backbone, and then you have your level 1 non-backbone areas that you can associate to it. We'll talk more about that when we get into the MPLS VPN section, where we're going to use IS to IS as our IGP. EIGRP, it has its own transport protocol, which is IP protocol 88, where it leverages RTP, the reliable transport protocol. And this is going to be the mechanism you're going to see later on, where there's going to be, in the debug output, you're going to see a UN/RELY for rely. So you're going to see, it's going to literally say something along these lines. You're going to see UN/RELY 0/0. And if you see this 0 turned on, it's referencing this. If you see this 0 turning into a 1, you're referencing that. So this correlates to this correlates to that. Okay, so now that we've gotten that under our way, what ends up happening is you are going to be leveraging a multicast through 224.0.0.10 to discover EIGRP, other EIGRP enabled routers on your same segment. So if I have R1 here and I have R2 here, and there's a link between the two on gig 1 here and you got gig 1 there, and it's 10.1.2.0/24, and you're using .1 here and you're using .2 here, If you enable EIGRP on 10.1.2.0 here and 10.1.2.0 here, that's going to enable EIGRP on the Gig 1 interface of both routers, and they're going to start being able to send hellos to 224.0.0.10, and once they discover each other and they form a full adjacency, then it's going to flip over to unicast to exchange all of the routing table information. In this case here, the topology information with what they call the TID list, with the topology identifier list. And that's what's going to end up allowing you to communicate the topology table with each router. So it does use multicast neighbors to discover and form adjacencies, and it uses reliable multicast with sequence numbers and acknowledgments to keep track of routing updates and things like that. And it uses unicast to synchronize the unicast routing topology. It forms active neighbor relationships, which guarantees packet delivery and supports partial updates. So you are going to, whether you do a debug or a Wireshark capture, you're going to see consistent hellos being sent over the wire every 5 seconds. So it's a 5-second hello and a 15-second dead timer, in case anybody was wondering on that. Guarantees a loop-free topology. We don't have a full copy of the database of the network, so we are relying on our neighbors to tell us everything about what they know. The interesting thing about this, where OSPF and IS to IS have what they call a link state database for OSPF, and you have a link state packet database for IS to IS. So when we talk about that, this is a database, right? This means that there is information exchanged between routers to make sure that everybody has the same copy. EIGRP doesn't have that. So because it doesn't have that, you're going to be relying on your neighbors to tell you about everything that your neighbors know about. Now the problem with this is it's what we refer to, I don't like to use the term colloquially, or however you say the word, routing by rumor. So just imagine, you ever played a telephone game when you were in school, where you get lined up, 10 kids get lined up in a line, and your teacher walks up and whispers, "The sky is blue," or gives you kind of like Sally sells seashells by the seashore, something along those lines, something that you'd have to repeat it specifically to the next person. So the teacher says it to the first kid, and then it goes down the line, and by the time you get to the 10th kid, it may not actually be what Sally sold stupid shoes to Sally Struthers or something like that. I know I'm coming up with something. Someone's going to make a comment in the comment section, I'm sure of it. But the point being is something got mistranslated or miscommunicated from the source to the receiver. So that is what they refer to as routing by rumor. And in most cases, it's pretty accurate. However, because it is a distance vector protocol, there's no guarantee, there's no database exchange between your routers. So you're hoping, praying, banking on everybody else to tell you what's going on. So in that particular case, you do what you can. So in most cases, it's good. I mean, over the 15 years that I've been doing networking, I can think of only a couple of times where I've had issues with, EIGRP on a very, very large scale, and we ended up breaking it up into multiple ASs, stuff like that. So dual is used, the diffusing update algorithm is what dual stands for, and it is used to determine the best routes and which paths are considered backup routes. So I'm going to put the term here, successor, and then feasible successor. The difference between these two is this is going to be your first route, this will be your second. And the reason why I say it that way is your feasible successor is going to be so you still have a path to it, but the path isn't the best. Is literally that's why they call it a backup route. Now, because it does this, we end up getting into the concept of fast convergence. Now, fast convergence is cool because it automatically pre-calculates a backup path. So you don't have to go into like OSPF and figure out how to do fast reroute or do BGP with prefix independent convergence or PIC or add path or anything like that. It's automatically going to detect this other path and it's automatically going to pre-compute it. So it's already good there. And EIGRP is pretty fast to converge considering what it can do. There is a granular metric, so it does have multiple K values. So K values are going to be how EIGRP determines how to figure out or how Dual is going to calculate the best route. So there are 6 of them. So you have bandwidth, delay, load, reliability, and MTU. There are other ones out there as well, and we will see what they look like once we get further into our discussion here. But by default, your bandwidth and delay are the 2 K values that you're going to reference, which I believe it is 1 and 3, but don't quote me on that. And then the K values are weighted, and I'll talk more about this in detail when we get into it. But by default, they all have a metric of 1. And then load, reliability, and MTU basically are, have a 0 attached to them for their weighting process. So by default, bandwidth and delay are the only things that EIGRP looks at when it comes to trying to figure out where do we go. So keep that in mind. So I'm going to have to go ahead and clear the screen. So if you haven't already done so, go ahead and take a screenshot of what I've got there. So I can scoot down here a little bit. We're going to wrap this up. EIGRP is the only routing protocol besides BGP that can do unequal cost load balancing. And you might say, how does BGP do it? Well, BGP can take advantage of it with MED, the multi-exit discriminator, or with, if you were to take, if you had, say, R1 and you had R2, and you have a loopback address, I'll say loop 0, and you have loop 0, and you want to form a multi-hop BGP peering between the loopback addresses, and in between R1 and R2 you had multiple physical interfaces. This could be 1 gig, this could be 2 gig, or something along those lines, and you could load balance over stuff like that. So the way that EIGRP does unequal cost load balancing is through the variance command. And the variance basically is load share. So of this load, how much of it do I want to share amongst the backup path? And then you can come up with you have to figure out what the math is on a particular backup path to see if you could actually get it to load balance. Now, secure neighbor adjacencies, this is where EIGRP gets kind of complicated when it comes to authentication. Now, when I say authentication, I mean auth. I do not mean encryption. So what's the difference between the two? What's the difference between authentication and encryption? Well, a very simple answer to that question is this. Authentication is going to be you having a key to unlock your front door or unlock your car. Or unlock your phone. It is not the same thing as encryption, where encryption is you're hiding the data. So, for example, if you've got a camera on your front door and you decide you want to, not be visible, you could potentially, be in an area, a blind spot in the camera. And encryption means that anybody that's sniffing the wire to see what's going on with your traffic, they won't be able to see what you're doing or what the data is. That's what encryption is. So we say authentication because you're authenticating the EIGRP header and making sure that 2 routers have the same password for a particular link. So that's essentially what that means. So I got pulled away from my computer for a little while, so I lost my train of thought. But the authentication is the validation of two or more EIGRP routers in the same LAN segment. So same /24, same /29, something like that, where the same password is used to exchange and authenticate EIGRP headers with each other. So you're not encrypting the data between devices, you are just simply authenticating that EIGRP speaker is authorized to operate on this particular segment. So that's what that means. So in classic mode, all you can do is MD5. We're going to take a look at both MD5 and SHA-256 in named mode. And then if you are looking to do even higher security EIGRP, which I've never seen in production, but I've demoed it a bunch of times, is keychains, where you can set a time range for a particular key with a particular password. And you can set the keys up for like once a month rotation. You change your EIGRP authentication password and you use a start time and end time, things like that. One of the cool things about EIGRP is the capability for engineering and traffic engineering and optimization. So you can do, from a traffic engineering perspective, you can do stub routing, where you can say don't send me queries if something happens in the network. So a query is if you lose a route, if a subnet in the network goes away, EIGRP will send out queries to all the other routers in the network to figure out, is there another path to that particular subnet. And if there is, great, it'll find out about it. If it's not, then you will go into stuck and active and until you get a response back. We'll talk about that more in detail in an upcoming video. But if you are the edge, so for example, you've got like your core distribution in your access layer, well, typically your distribution is going to be where all of your SPIs sit. So you would turn EIGRP on for the SPIs, but you wouldn't form any adjacencies with SPIs with another switch. So by doing that, you would go what they call passive interface at the SPI level, and then you would also say stub, and the stub route would go up and tell the upstream devices there's nothing southbound of me running EIGRP, so don't even bother asking me, sending me queries and things like that. It's basically it's a way to control the query domain. Summarization is taking, say, 3/24s, or actually, let's do 4/24s, and advertising them as a /22, for example. You could summarize the EIGRP. You can also do ACL filtering to prevent specific routes from coming in, and then doing route manipulation. You know, I don't want to have this particular route come in, I don't want that particular route to go out, things like that. So we'll take a look at how this comes into play down the road. But essentially, that is what you need to know for EIGRP to do its job. And that's a high-level overview of what the capabilities are and stuff like that. We'll get into forming adjacencies in the next video and how all that type of stuff works. I'll go into that level of detail and we'll talk about those things. So until next time, guys, if you haven't already done so, please drop a comment in the comment section below. If you haven't already done so, please like, share, and subscribe, and I'll catch all of you people in the next video.